Is there a specific reaction to convert an alkene to an alkyne? Well, it depends on the nature of the alkene. So if you have a non-functionalized alkene like trans 2-butene, there's no way to go directly from there to there. What you'd actually have to do in this case is use an intermediate like bromine. So do the dibromo, and then you use something like NaNH2 to completely deprotonate. If you have a functionalized alkene, and ideally in this case you would need a halogenated alkene, then yes, you could do it, just skipping to that step. But as far as non-functionalized alkenes go, they have to be functionalized in order to get you back down to that alkyne. Sorry. But yeah, there's really no way to go directly from a purely hydrocarbon alkene to an alkyne. You're gonna have to functionalize to get it further down. Because the thing is, you need a leaving group. Now, the other thing about this is that you don't want to go through an alcohol, and it's kind of talked about next in organic too. If you have something like this is called an enol. Enols don't actually exist for most alkene compounds. Typically, what you get is the ketone. So don't go through an alcohol intermediate, otherwise you run a really major chance of creating an enol, and which will tautomerize into a ketone, and you just can't react those into alkynes. At least not easily. You're welcome. So just a reminder, since no one's really asking questions right now, your lab practical is next week. It's going to be online under the quizzes and assignments. It's 9 questions. 8 of those count towards points. There's one thing for extra credit. This is completely open resource. The big hint I'm going to get for you is that I've already told you where I get my spectra from. So if you're questioning, like, I'm not sure if my answer is right on a spectrum, you can use those databases. This is an open resource practical. So if you sit back and say, well, I wonder if this is really the IR spectrum of this, go look up the NIST, go into NIST chemistry webbook and go look up and verify. This is open resource. This practical will probably, I was skimming through it this morning, probably not going to take you more than an hour of your time, especially if you're just being kind of judicious and really just thinking about the problems. There are no gotcha questions on this practical. It's very much meant to be a straightforward, do you understand the basics of an organic chemistry lab, and do you understand the basics of the analysis? Now you also have the second lab report up, which is you generating questions for the 5 test areas. Go ahead and knock that out. Not gonna lie, I'm gonna shamelessly use your questions if they're good, but that, or you'd have to write a lab report on the last lab you did, which was a complete and utter disaster. So this should help you. One thing I found when I teach courses is that when I try to develop problems, it does a very good job of helping me think through the process, think about how the questions would be interpreted. This is honestly an exercise that really is considered good pedagogy for teaching students, making you come up with your own questions. Big reason we don't do it practically is just it's very time consuming for us to do it. So to get all of you to come up with questions tends to eat up a lot of your time, eats up a lot of our time to go grade them. So this is actually a best practice for teaching. It kind of works. Normal semester, I typically wouldn't do this just because it is a lot more involved on both your part and my part. So one of those, if this was the only class you were taking and this was the only class I was teaching, this would be a fantastic way to teach you. But the hard reality is I teach another section of chemistry too, and reality is y'all have classes other than mine to work on. But yeah, do use this as an opportunity. You're going to find this really does, for this second lab report, this is really going to help you reinforce the material to yourself. And feel free to go as in-depth into the questions as you want. You don't have to produce spectra if you don't want to. Well, I mean, you do have to do it for the test one material, but see how clever you can be and how well you can figure it out. Again, all my resources are available under that course announcement. The NMR simulation software, the IR databases, the mass spec databases, play with them, get more familiar with them. Now that you know kind of what to expect, you're going to be a little bit more comfortable working with the software. There's going to be less surprises or less confusion as to if you got what you really should be getting. People are a lot this morning. Okay. Form of the alkoxide needed for the William ether synthesis. Okay, give me a minute to bring up my notes to make sure I don't tell you anything wrong about this. But if I remember correctly, the Williamson ether synthesis, typically you're going to use one alcohol and you're going to deprotonate it. So this way you're pretty much guaranteed the right ether. But again, let me make sure I'm telling this to you correctly. There is a lot of there's a lot of dark magic associated with making ethers, and it's one of those things, if you put too much thought into it, you'll begin to realize why what we say about ethers doesn't make a ton of sense. Okay, so I'm thinking about it right. So for the Williamson ether synthesis, the nature of the alcohol isn't particularly important because you're not going through a carbocation intermediate. You don't have to worry about forming the carbocations. You don't have to worry about rearrangement. So you can do this for primary ethers just fine. Ideally, though, so you've got your alcohol. Typically, you're going to react it away with something like sodium metal, and this will give you the alkoxide. What you would prefer synthetically is that your alkyl halide looks like the alcohol you're working with. The big reason for this, and you may have seen this in the notes, this can be driven, but this is actually a reversible reaction. And so if you don't have in this case, if you don't have an ethyl group, you have a propyl group, yes, the first ether you're going to form is going to look like ethyl propyl ether, but this bromide can come back and attack either side. So it can attack the ethyl group and it can attack the propyl group. And because of that, you could recover 1-bromoethane or 1-bromopropane. And in this case, eventually through equilibrium, you would get a mixture of the diethyl, the dipropyl, and the ethyl propyl. So again, to kind of backtrack to your question, the alkoxide, it doesn't matter, but you want the alkoxide and the alkyl halide to basically be the same thing, with the alcohol basically being where the bromine is. This way you're guaranteed to get a symmetric ether. Yeah, you can do it with asymmetric ethers, just understand you're going to get a mixture that you're going to have to separate back out. The longer you let it sit, the more and more mixed up it's going to get. So there's just more practical sides with the Williamson ether synthesis. Actually, it would kind of be cool to set up a lab. So one thing we don't ever really cover in Orgo 1, and I would love to talk about, is what's called reactive distillation. So in reactive distillation, you're using the distillation to drive a reaction. So with a normal distillation, you're separating two or dozens of compounds together. In the case of reactive distillation, you're using the distillation to remove one component of a reaction mixture that's equilibrium limited. So basically, you're driving Le Chatelier's. So to do something like do an ethanol propanol mixture with acid and distill it, and the high weight ether will remain behind, whereas the water will distill off, and so you can create a really high purity ether, and then turn around and get you to do the reverse, to actually try to break it back down into the ethanol, the propanol. So that might be something to look at for organic one labs. Biggest problem would be it's a distillation, so there's going to be a lot of downtime. But it would be cool for you to actually see how reactive distillation works. It's something that even regretfully, even chemical engineers don't talk about that much, even though they're so horribly practical. And it would be a great demonstration of the Chatelier's because you're using the distillation to drive off the water. And ideally, if we formed an ether that was hydrophobic, it would be a lot easier for you to see it. So you would actually see as it begins to distill, you begin to separate off the layers, and you would create the water layer and the ether layer. Biggest issue we would probably have with that is that we're simply generating ethers. There's a bit more associated with disposal with ethers, but again, if I could give you something like an acid catalyzed decomposition of the ether, that'd be kind of nice too, because the acid decatalyzed composition creates a mixture that we can pour down the drain. So yeah, I should probably write that down. Big cool idea. Step number 2 in today's lab discussion board. I thought today's lab discussion board was prep for well, this week's discussion board should just be a review for the practical. So are you talking about the April 21st lab discussion board or the discussion board for April 28th? So I'm guessing it's the one for April 28th. April 28th. Okay. So the step 2 is that you want to get to this terminal alkyne. And you're going to start, it's actually 2 steps involved with this synthesis. Now, the thing is that we want to preferentially eliminate from the ends. So we're trying to get rid of the hydrogens that are down here in the CH3 groups. To do that, we have to basically force it so there's no other hydrogens to pull from. So we need to somehow engineer this molecule that when we do 2 eliminations, we only have hydrogen to pull off the ends. And the easiest way to do that is by adding 2 bromines. Because if we add 2 bromines, you're going to both add across that triple bond to give us this. Now, if we want to do an elimination, we'd use a super strong base. And in using this super strong base, the base is going to abstract a hydrogen. Well, the only hydrogens that can be extracted in this case are the ones that are sitting here on the methyl groups. So these 2 hydrogens are going to get eliminated in order to form this triple bond. These 2 hydrogens are going to get eliminated to form this triple bond, and this is how you end up with this conjugated alkyne. But the trick with this one is seeing that if you do any type of substitution, let's say you did HBr. So if you do 2HBr, you'll get this compound. And when you go to do an elimination, you're going to eliminate from the most substituted carbon. So this is, again, a Zeitzet's rule situation. Something like NaNH2 is going to pull from these two hydrogens, and you're just going to recover right back here. So the only way to force this reaction to give you the terminal alkynes and the conjugated diines is to do the 2Brs or 2Cl2s or something to that effect. Yeah, I hope this was a pretty. Hopefully, it wasn't too like obtuse how you get to the point of doing this. But yeah, the big thing was just getting you to think about where the hydrogens were going to go. But that's fine. Yeah, thanks for letting me know. Again, the discussion boards are always meant to be open. It's just for attendance reasons I have to record that your absence if you don't do them on time. But informally, we're not dropping any students this semester. That's not an official policy. It's an unofficial policy. Summer is going to be different because those are truly online, and it's also looking like fall is going to be truly online. At that point, yeah, if you're not hitting the discussion boards in a timely fashion, then we do have to withdraw you. But as long as you're doing them, that's what's more important to me, is that you're doing it and you're working through it. And hopefully a lot of you are looking through the feedback I'm giving you, especially if you're not getting full marks. I do try to put comments in there to try to kind of help you out, and please go back and figure out what's going on. I really want to make sure you understand the material, particularly if you go into Organic 2. I want to make sure you've got that foundation ready to go. Now, I am teaching Orgo 1 and Orgo 2 this fall. I'm also been put in charge of basically converting our Organic to onlines. So the guidelines for lab report number 2. So to help you out with that one, give me just a minute. Let me switch into student mode on Blackboard, because there's things you can do in student mode that I can't do. So if you go under My Grades, and you got lab report number 2, there's a view rubric. And this is going to map out for you what the expectations are. So for 5 questions, 5 points, or for 20 points total, Overall, those 5 questions need to address all 5 areas. So they don't necessarily have to do them in isolation. So if you want to use test 1 material for your test 3 question, that's fine. But the point is that with all 5 of these questions, ultimately you have to address all 5 areas. We'll go through the description in just a minute. Another one is making sure your solutions are correct. And the other thing is making sure that what you've given me is fairly intelligible. I mean, I've been trained to do the online component, so not necessarily something that I could just copy and paste and use directly, but mostly so it's clear to me what you meant to say. Now, in terms of the description of the assignment itself, so things like, oh, it looks like I'm missing a 5th area. Alkynes and ethers, alkyl halides. Alkenes is missing from this description, so that may be your confusion, but there needs to be 5 questions. One about organic characters and structuralization, one about alkanes, one about alkenes, one about alkynes and ethers, and one about alkyl halides and alcohols. And yeah, the question you submit needs to have an answer. So, any other questions so far? So Christian, let me know if I didn't answer your question sufficiently. Nicole's asking for last week's lab discussion, step 2. So we'll go back over that. So with step 2, make sure I got your question out. Oh, last week's lab discussion. Oh, that's a different question. So in terms of the transition to, so the question is that in that previous lab discussion, you had this reaction. And you had step 1 with its products and step 2. So step 1 was your H2O Br2. Step 2 was your H2SO4. And the question is that there were 3 products that were described here, and did we need to use just one product if we need to use all 3 products? The answer is actually it doesn't matter. And the reason it doesn't matter is that you will get the same, basically you'll get the same answers. So there were 3 possible products here. You had the alcohol, you had this, and you had the intended product, which this was the alkyl halide with the alcohol. Now, the H2SO4 is going to perform an elimination. So if we do an elimination on that one, we'll get our starting compound. If we do an elimination on this one, if we do a single elimination, we'll get that product. If we do a single elimination on this, we'll get this product. And if we do double eliminations, we'll get these products. So ultimately, you don't really see much of a unique product here. And this is more what it's getting at, is that you probably would have done a single elimination or a double elimination. So I hate to kind of give you a roundabout answer to that, but really it didn't matter which one you picked. The one I worked off of was the desired product, and I probably need to specify that when I talk about it in future courses. Really, you could use any of them, but I should probably sit back and say that you should work with the desired product. And honestly, that would probably be a better problem if I worked with a different starting alkene. So probably this fall, I'm going to change the starting alkene to be something that's the dimethyl. the 1,2-dimethyl, because it would be a bit more selective in its products. Now I'm sitting up here thinking you'd probably more likely, yeah, it'd be a lot simpler if I switched to a better alkene. You're welcome. All right, what else you got for me this morning? Or what else do y'all have for me this morning? So if you're looking to take Organic 2 this fall at Wake Tech, we are offering it online. I'm teaching it. I think there's another teacher on North teaching it. We're assuming at this point we're teaching online. For the Orgo this fall, there will be take-home lab kits for roughly 3 to 4 labs for Orgo 2. I'm looking to partner with NC State that have a few virtual labs. The software is a little clunky, but it's also hard to tell if it was clunky or if it was just me messing around with too many things at once. But it will be taught online. It will have a lab component associated with it, and it is meant to be the equivalent of a seated Orgo 2 course. I'm leading the organic conversion, or the online conversion, so there will be videos, online packets. We'll still be using the McGraw-Hill textbook, still be using the Carey and Francis book. So if you need Orgo 2 and you want to take it to Wake Tech this fall, it is available. And yeah, the plan is by the summer to have a deployable, intended to be online course ready to go. All right. So if there's no other questions, we'll take off early. Like I said, I tried to front end this class, so this way the material between now and the end of the semester is pretty straightforward. Don't forget, Finish your alkyne ether homework. That's going to be 70% of your final exam grade, with remaining 30% going to the review materials. It will be a 30-question multiple choice exam. You get to take it twice. The second time, it will let you go back and correct your answers. I don't necessarily know if it's going to tell you if your answers are right or wrong, but it will give you the option to go back and check it. So, other than that, I will see y'all this Thursday. All right, take care, and thanks for showing up.